All right, Illustrative Math, Unit 2, Lesson 17 is called Graphs of Rational Functions, Part 1. So our goal today is I can identify a vertical asymptote from a graph or an equation of a rational function. So as you look at that goal here, the first word that probably pops up is a vertical asymptote. What the heck is that? So if you look at this graph here, and I drew a couple examples here, the asymptote is like an imaginary line, so they make it dotted that your graph gets really, really close to, but never actually touches. So if I look here, as I trace this graph from left to right, it starts shooting down towards negative infinity, getting more and more negative, but it never actually touches that dotted line. It gets real close to it. And same thing here, as I trace this graph from the right, it gets really close to this line here at A. Okay, now this one is going in opposite directions. This one here, they're both going towards the positive direction. But the line x equals a is the vertical asymptote for a function f if f is undefined at x equals a. All right, and then you can pause the video and read the rest of this. But what I want you to realize here is undefined, this comes from when basically your denominator equals 0. Okay, so if I had a function here, let's call this f of x equals some polynomial up top. Okay, I don't care what it is. But if the bottom I had x minus 1, let's just say. All right, we're going to have a vertical asymptote. I just like to abbreviate it as VA. Vertical asymptote is x equals positive 1. Because if I plugged in 1 here for x, I'd get 1 minus 1. That would give me 0 in the denominator, which is not possible. You can't divide by 0. So, another technique is you could take the x minus 1, if you can't see it or mentally do it, and just set it equal to 0. Solve that equation. Boom, we get x equals 1. So obviously, if it was x equals a, like I had here, my vertical asymptote would be at x equals a, and then I would add a to both sides, and that's how I would get that. Okay, so a is the x equals a is the vertical asymptote, and x minus a would be what's giving you 0 in the denominator. Now, also make sure you understand when it's x, the equation of the vertical asymptote is x equals a. It's not a. A lot of kids just say, where's the vertical asymptote? And they answer a. Well, no, it's the equation of a vertical line. Vertical lines are always x equals, and then the basically the value that it crosses the x-axis, or really the value that all x coordinates on that line are. Okay? All right, so here's our warm-up. So what I want to use for the warm-up is an old equation, distance equals rate times time. So Kieran's aunt plans to bike 10 miles. How long, so that means we're looking for time, will it take if she bikes at an average rate of 8 miles per hour? So this would be my D, and this would be my R. So if I wanted to solve for time, I could divide by R. So I would get D over R equals T. And so for this one, I could say, okay, my distance is 10 divided by my rate of 8. That'll give me my time. Okay, so that would give me 1.25 hours equals the time. Okay. If I go to the next one, how long will it take if she bikes at an average rate of R miles per hour? So I'm still using this because it's asking for how long. I want it solved for T. So I'm going to say T equals your distance of 10 divided by R. There it is. So this is a rational function because we have a variable in the denominator here. And basically, you couldn't plug in 0 for R because I would have 10 divided by 0, and your calculator would freak out and give you an error. So we're going to get that asymptote there when we have the variable in the bottom. Kieran wants to join his aunt, but he only has 45 minutes to exercise. What will their average rate need to be for him to finish on time? So this time we have the time. We know our distance still, so let's do this. Distance equals rate times time. what will the average rate need to be? So this time I'm going to divide by t. So distance divided by time will give me the rate. Now I want to stay consistent with my units. This is in minutes, and the rate is in miles per hour. So why don't we do this? 45 minutes divided by 60 minutes is 0.75 of an hour. So I'm going to use 0.75 for t. So 10 divided by 0.75, that'll give me my rate in miles per hour. Okay, so when I divide it out, I think I get 13 1/3 miles per hour. Okay. What will the average rate need to be if they have t hours of exercise? So this is going to be the same thing. We're looking for r. So r is going to be 10 for your distance divided by t. Okay, so that's nice because then you could plug in any time there and boom, you could find your rate. All right, Kieran plans to bike 10 miles. Write an equation that gives his time t in hours as a function of his rate r in miles per hour. So we want t of r. Okay, so remember, distance equals rate times time. That's where we're starting with. We know our distance is 10. So we want to divide by r, or let's use a lowercase r. Oops. I guess it doesn't matter if I use a capital R or a lowercase r. Just want to make sure I use the same variable. So let's do this. Let's call it t of r. Time of r is equal to 10 divided by r. All right, so let's graph this. So I already have it graphed. It's going to look like this. Now notice I did not have negative axes because think about your variables. Distance, rate, time. None of those would make sense to be negative. So remember, it's important to look at what you're looking at here. It's t of r. So this is my time on the y-axis, and this is my rate. And remember, this is in miles per hour, and this is in hours. Okay? So basically, as the time that it takes him goes down, or as the I should say, as the rate goes up, the time goes down. Okay, so the faster Kieran rides their bike, the lower the time is going to be. All right, what is the meaning of t of 8? So that's the time it would take if she rides at 8 miles per hour. Okay? So does it make sense? Explain your reasoning. So I'm going to plug that in. I'm going to say 10 over 8. So I'm going to say t of 8 equals, so that would be 1.25 hours to go 10 miles in, or at, I should say, not in, at 8 miles per hour. Okay. What is the meaning of t of 0? Does that make sense? So that would be the time it would take if she rides at 0 miles per hour. Well, that doesn't make any sense because if you ride at 0 miles per hour, you're never going to finish 10 miles. So I would say no, you'll never finish. Okay, if you're riding at 0 miles per hour, you're never going to ride 10 miles. And then 5, as r gets closer and closer to 0, what does the behavior of the function tell you about the situation? So as r gets closer and closer to 0, so as I move close, so r is right here on the x, as I get closer to 0, and I'm not coming from this way because there's no function over here because you're not going to have a negative r. As I get closer to 0, my time is longer and longer. Okay, so the behavior of the function, the time gets longer and longer. So on a graph, it goes up, which is towards infinity. And that's the abbreviation for infinity. It's like a sideways 8. How about this one? As r gets larger and larger, what does the end behavior of the function tell you about the situation? So as r gets bigger, so as I get bigger and bigger, as I go this way, if this is my arrow, that's a terrible arrow. Let me redraw that. As my function goes to the right, what happens to the time? Well, the time gets smaller and smaller and smaller, closer and closer to 0. Okay. As the rate, or r, gets bigger and bigger, the time gets closer to 0. Now it'll never equal 0 because you can't teleport, but it's going to get closer and closer and closer to 0. And it will never be negative either, because you're not going to have a negative time. All right, so here's a notice and wonder. F and G are both rational functions. So here's F, here's the function, here's the graph for F, and then here's G, here's the graph of G. What do you notice? What do you wonder? So I would say I noticed that they both have vertical asymptotes. If I look at this one, F, it's at x equals 0. G is at x equals 1. So what do I wonder? I also noticed that they look exactly the same here, meaning if I were to like kind of trace this right here, it's kind of the same shape. It's just moved horizontally. So this is x equals 0 is my vertical asymptote. This is going to be x equals 1 is my vertical asymptote. They both also actually have a horizontal asymptote. So if I look right here, here's my horizontal, meaning my graph gets closer and closer to that. Here's my vertical asymptotes. There's the vertical. There's also horizontal. We're not going to do too much with horizontal asymptotes today, but we will get to that eventually. All right, so here we go. We're going to match some of these now. I took a few cards out. You might be wondering why I skip like E and F. There were a couple ones that were blank graphs and blank functions. Whoops. So I've taught this lesson before, and it was just too confusing. So right away, you should notice if you look at B and G, see how they're flipped? I'm sorry, not B and G. Whoops, I said that wrong. C and D. Do you see how they're flipped from all the other ones? And you notice right here, R and N have negatives. So that's going to tell you right now, should figure out, since there's two of those that are flipped, if the function is negative, it's going to flip it so that it goes opposite of what we've been doing. So kind of use what I taught you about the asymptotes. This one's going to have a horizontal asymptote at x equals 0, and so is this one. So I can match it up here. My x equals 0s are, actually I have 3 of them here. I have 1, 2, 3. So let's do this. Let's take the one that's flipped right here, D and R. You see how my asymptote here is at right here at x equals 0, right there on the x, or right there. It's basically the y-axis. But you see how I'm backwards? I know that's going to go with the one that's negative. So I'm going to group these two together. Let's go here. The other negative one, if I look right here, my asymptote is at x equals 2. Because if I plug in 2 for x, I get 2 minus 2 is 0. Can't have 0 in the denominator. So that's going to go with C. So that'll get rid of some of these and make it a little bit easier. All right, let's do this. Let's narrow this down here. Here's the 1 over x and the 12 over x. So both of those have So that's going to either be B or G. So what I'm going to do is I'm going to say B looks the same width, I guess, as D. If you look here, these look exactly the same. See how G is a little bit wider? So I think this one's going to go with P of X, basically because the same function, they're just flipped. All right, and I know that asymptote is at X equals 0. So that makes me think that, whoops, hold on. That makes me think that this one goes here. So last two. So it's kind of the same idea. These both have an X equals -2 for a horizontal or a vertical asymptote. So the one that is a little bit more narrow here kind of looks like the other ones that have a 1 in the top in the numerator. That one looks like that. And then this one is going to go over here with A because it's a little bit wider. Okay. And again, if you wanted to plug these in on Desmos and take a look at them and play around with what happens, like if this number gets on the top gets bigger and bigger, you can see how wide it gets. The asymptote does not change though. You can play around with the negatives. You can play around with different numbers in the bottom. It'd be kind of a good little activity to do. All right. Lesson synthesis. I'm not going to go through all of these here. I'm just going to maybe do a couple here and just kind of take a look. So this looks like, they didn't show us that it's 1. I'm going to say it's 1. So this is my vertical asymptote here is at X equals 1. So that means in the bottom, I'm going to have X minus 1. And then in the top, it's not really wide, so it's probably like a 1. I don't know for sure, but that's going to equal f of X. Okay. Now this one's almost the same. It's just flipped. So what's going to happen here? Oh, the asymptote's different though. Let's say that's at 3. So here your vertical asymptote would be X equals 3. This function called f of X is going to be 1 over X minus 3. But then since it's negative, or since it's flipped, it's going to be negative. This one here, my vertical asymptote's at -3, so my vertical asymptote is X equals -3. Function 1 over, it's going to be X plus 3. Okay, and it's not flipped, so there it is. All right, maybe do 1 or 2 more of these. Maybe go, let's go to this one, E. So E looks like my vertical asymptote is X equals 7, and it's not flipped backwards, so my function is going to be 1 over X minus 7. Okay. Now, do I know it's a 1? Not necessarily. I'm just kind of estimating it. It could be a different number, but we learned the bigger this number gets, the more wider that gets, less of a right angle. Okay. And I'm not going to do the rest of these, but all right, what type of descriptions were helpful in identifying a graph? Obviously, the asymptote. Obviously, if it was a positive or negative. Graphs like A and B have the same asymptote. How do you know which one your partner is talking about? Well, you would need to know the number in the numerator, figure out how stretched out it is. You'd need to know if it's negative, to know if it's flipped. These graphs are all either positive or all negative, depending on what side of the vertical asymptote they're on. Do you think? So I basically answered all these questions on the last slide. So I'm going to just kind of skip ahead. So goal, I can identify a vertical asymptote from a graph or an equation of a rational function. I think so. Cool down. The student council has $800 to spend on homecoming t-shirts. The number of t-shirts they can buy is a function of the price of the shirt, P in dollars, given by N of P equals 800 over P. So here's your graph. As P gets closer to 0, what does the behavior of the function tell you about the situation? So P is on the x-axis. As P gets closer and closer to 0, the price, P is price, the more and more t-shirts you can buy, because Y is, the price of the t-shirt is P, and and then this is dollars. So this is dollars, and wait, no, that's not right. The number of shirts. The number of shirts. So we'll call this S for shirts, and this is price in dollars. So as the price gets smaller and smaller, the more shirts they can buy. So as P gets closer and closer to zero, the number of shirts shoots way up. So I mean, think about it. If you got $800 to spend and you can get shirts for a penny a piece, you're gonna be able to get a lot of shirts. If they cost $100 a piece, you're not gonna be able to get as many. So on this one, I would say here, the cheaper the price per shirt, the more shirts you can buy. As P gets larger and larger, what does the end behavior of the function tell you about the situation? So P keeps getting bigger and bigger. I would say as P gets larger and larger, the number of shirts you can buy gets closer and closer to zero. Notice I didn't say smaller and smaller because that would imply that I would maybe be going negative. So I'm just going to say it gets closer and closer to zero because I'm you can see it flattening out. It's not going to cross this line here. I'm not going to, if my graph was here, it's not going to go down here past that on the x-axis. I'm not going to get smaller and smaller. I'm going to get closer and closer to zero. Okay, so there you go. All right, hope you enjoyed this lesson. Thank you for watching.